Good day, and you're all very welcome to today's CNPS technical session. We're delighted actually to have back with us James Arathoon. And in fact, since he's based in Wales, I said good day, but I'll also say you're not da, which in Welsh is good day. He's based in Aberystwyth. And he's going to talk to us today on a discussion of the fundamental nature of the physical constant alpha, which is the fine structure constant. And this basically is the constant that quantifies the strength of the electromagnetic interaction between elementary charged particles, hence its fundamental nature. Now, James has given us a few lines, introductory lines, if you like, about what he'll be talking about today and the structure of his talk, which I think it would have been too much to put on the announcement, but it's useful just to describe very briefly what he's proposing to do. It's a rough outline. So he has introductory slides, which he'll be starting with. He'll then be talking about the basic properties of the electron and light. He'll then be delving into the fine structure constant, some theoretical approaches. Now, he has two case studies. The first one he calls Case Study A, which is the Bergman-Wesley electron model of 1990. He'll then be looking at measurement and observations of alpha. Alpha is the symbol for the fine structure constant. He'll then be going to case study B, which is the quantum Hall effect. And he then questions, feedback, and discussion as normal. Now, the quantum Hall effect is strongly related to content introduced earlier in the talk. And he's proposing to add, as case study B, a video. Now, this video, I've had a look at it myself. It occupies about 20 minutes, and it's given by a Professor Stern in Israel, I think. Now, unfortunately, Professor Stern's photograph appeared on the initial announcements to the lecture rather than James's. And I might say James is a younger man and slightly more good looking maybe than Professor Stern, but I think it's been updated perhaps in the most recent submissions to YouTube. So we'll have a little less time for the talk properly. Actually, James added one more thing. He says in this lecture, H over E squared is mentioned in the video. It's the von Klitzing constant, an impedance measured in ohms, and the fine structure constant is given by the ratio of the impedance of free space divided by twice the von Klitzing impedance. This impedance ratio will be introduced earlier in the talk when talking about electron models, particularly the Bergman-Wesley electron model. And James says he knows that this model is ultimately flawed, but I think it more useful to discuss in detail than others I have encountered, particularly in trying to find linkages between different measured phenomena. I think James also thinks that a lot of us are very knowledgeable in electrical engineering. I think some of us are, maybe not all of us. So rather than occupy more time, I'm going to bring James up. There you are, James. Good afternoon to you.
Oh, yeah. I'll just put my...
So...
Just a second. Right.
Yeah.
Can see my picture
take your time. Okay. We talked about your photograph being your video a little washed out, but I think it's visible. There's no problem about that. And you might want to say a few introductory words or correct anything that I said. Maybe.
It's basically I'm not an expert in these matters, but I have been exasperated by the level of or an approach to the fine structure constant in videos which try to present physics to the general public, in the YouTube, etc. And so I want to try and, rather than being exasperated at the mystery of it all, try and do some calculations and see, even if we get wrong answers, to see where we might lead to if we carry on and modify these sort of models. So that's basic premise, and hopefully people enjoy it and can criticize and maybe put their thoughts at the end.
Yes. So you'll probably be speaking for, a little less than an hour because of your.
Yes, I'll try and keep.
If you want to overlap, or there's no problem at all. There'll be just more time for questions and answers. So we do that, and as usual, I'll try to be scanning the questions coming in. If anything is very specific for James, do say that at James or something like that, because otherwise we'll just take it as maybe conversation between two people and we might miss it. And then we'll go to the green room. I see people are already coming into the green room, so we deal with that. So I'm going to bring myself down. Do you want to share your screen first, or do you want to do that in a few moments' time, James?
Yeah, we'll go to the screen and we'll just run through that. And yeah, we'll go to the screen.
Okay.
I'll put on.
If you can do what we rehearsed 10 minutes ago,
So
I have a little thing which I can bring up then. I don't have it yet. So just go into present entire screen and then click on the screen and I'll get it up and I'll put it up whenever you wish.
Right, it's up now. So
okay, I don't. Oh yes, yeah. So do you want me to put it up now, or shall I wait until you give the?
Yeah, put it up now, and we'll carry it. We'll start now. And
so what I'm going to do, James, if this is all right, is I'm going to disappear myself.
Right.
Which means I'll be in the background. If you want me back, just call, and I'll maximize the screen size so your photograph will probably disappear, and you just tell me if you want to. But you have complete control now. Okay.
Okay. Can you see the slides now?
Yes. Perfect.
Right.
I'm going to maximize them now.
Okay. Hi there. As I said, when designing this talk, I was minded not because I was an expert in the fine structure content, but I basically am interested in the constant and want to find out more. And when you look at the available information and the videos online, it all seems a bit in between, sort of mysterious and unexplainable to numerical, sort of people doing numerology to calculate this fine structure constant. And so we'll continue now. But that's my motivation. So let's do. Right. So a discussion of the fundamental nature of the physical constant alpha, known as the fine structure constant or the Sommerfeld constant. Arnold Sommerfeld was the guy who introduced the constant into physics. It was a modification of Bohr's early quantum model of the atom in 1916. Right. So, as I said, Ian's gone through that basic introduction, so I won't do it again. Right. So this is the fine structure constant as defined, and so alpha is e squared over 4 pi epsilon naught, which is the permittivity free space, divided by h bar or h, depending on how you want to do it, and the velocity of light c. H is the Planck's constant. H bar is the reduced Planck's constant, as shown. Is I think people should be familiar with that. So that's a definition. That's how it worked out in terms. This is the dimensionless number because all the dimensions cancel from the calculation, and it's the only dimensionless number you can make with these constants of nature. Right, so some values. I'll leave that on the screen for a few seconds. People want to reference it later on when they rerun it. Okay, so I just wanted to say why it's fundamental in physics, but also in measurement theory, because I mean Ian will know more about this than me. But the new SI system of units puts the fine structure constant right at the heart of the measurement system now. Basically, everything's defined now. I mean, originally the change was the speed of light was the only fixed defined constant, but now Planck's constant and the elementary charge are fixed as well. So the meter standard is set by the speed of light. The kilogram standard is set by fixing Planck's constant. The ampere is set by fixing the elementary charge. And alpha, a measurement of alpha, sort of knits everything together in a way. So the measurement of the fine structure constant becomes a very important part of the new SI system. And these are values, the latest I could find. And originally, mu naught used to be defined as 4 pi 10 to the minus 7 h, or Henry's per meter square, per meter. Sorry, and I mean, if you notice, it's still within the error bound to be 4 pi, but is actually calculated now and could be different from 4 pi times 10 to the minus 7. So epsilon can be calculated from mu just by the standard formula. So right, so as I say, the new system of units defines everything apart from mu and alpha, which are determined by experiment. You can, I suppose, try and measure mu on its own, but that's not normally possible. So they tend to measure alpha and then define mu from that measurement. Alpha is about 0.00729, which is about if you put 1 over alpha, it's about 137. Not quite 137, just over. And obviously, people are totally baffled as to why it has that precise value, and it seems to be fine-tuned for us to live in the universe as currently designed, if it is designed. Right, basic properties of the electron and light. So it's, as I said, it's dimensionless constant, and it's related to the interaction between electron and light. So we don't know yet whether it approximates to a notional irrational number in geometry like √2 or pi. We don't know yet whether it can be mathematically calculated using an algorithm independent of experiment, because that hasn't been found out yet. And the question of whether it's constant throughout the history of the universe, or does it change in time and space, is a question that a lot of people are interested in, and I'll come back to that later. So these are fundamental questions, and it's sort of whether it is a mathematical constant or whether it's purely a physical and rational constant. Right. I talk a lot about dimensional analysis. I did a video previously on dimensional analysis, and I've just split the history of the subject into 3 or 4 elements, and there's the pre-Bridgman, and Bridgman wrote a famous book called Dimensional Analysis in 1922, and so it was Fourier, the French mathematician, came up with a concept in the 18th century, and until about 1922, it didn't have a name. Bridgman named it, and after that, the subject matures. There's a lot of debate in the literature between, I mean, earlier than 1922, but up until about 1950, 52, and I've just put a good book on dimensional analysis, which sort of ends that debate, which is the Faucon book, Dimensional Methods and their Applications. And in the present day, we have an orthodoxy, and that orthodoxy doesn't include relativity. And I tried in a previous video to try and question why. Now, so what is a dimensionless number? It's just a ratio of two physical quantities, measured physical quantities, say 5 meters and 3 meters, and we put 5/3, no units. Now, a measurement is itself a ratio, but we put units on because we have one of the measures in that ratio is a standard, say a standard length or a standard velocity or whatever. And so in order to be able to compare one measurement with another, we have to reference that standard. So we say 5 meters, which is say 5 of a standard meter length and 3 of a standard meter. So, but when we take 2 of those measurements and create the ratio of them, we end up with a number with no units. And so strictly speaking, whatever unit system you use, you should those 2 identical physical measurements should come out at the same ratio with no units. And that's basically the idea. So and that's what I say at the bottom. Right, so we can do this, for example, with the ratio of a circumference to diameter. And I mean, pi is a mathematical notional number. I call it a notional number, much to the annoyance of mathematicians. But we can never specify exactly pi because it goes on forever. The number of digits is unbounded, infinite if you like, and we can measure only approximations in physics and engineering. So the circumference never precisely equals the mathematical constant, but will tend towards that the more and more accurately we make the measurement. Oh. Right. So dimensionless numbers don't need to be constant. It's hard to say why because they can depend on the scale of something. I'll come back to this in a second. So we're calculating approximations to pi. We can create n polygon system. There's lots of ways of creating approximations to pi, and you'll be familiar with your own examples. So we can gradually create more and more polygons, and then we'll gradually get more and more accurate, more and more triangles making up the polygon. So higher n polygon, and then we can gradually approximate more to the value of pi. So we've no agreed theoretical method for calculating approximations to alpha, assuming it is an irrational number like pi. Right, here we go. Interactions between electron and light. This is philosophical, but I think it's important, this bit. The alpha is dimensionless constant, somehow related to the interaction of light with the electron. But how does it interact with the electron? And there's various models, and I've put them into classes of models. So the class 1 model is the ratio of 2 intrinsic properties to the electron, e.g. the ratio of the speed of the electron in its orbit around the atom in ratio to the speed of light. I mean, this is referencing the Bohr-Sommerfeld 1916 hydrogen atom model. That's no longer accepted now, but it was the original definition of alpha. It's a fantastic piece of work, and it's a pity it was wrong. Using one intrinsic property and one extrinsic property. An example of this would be utilizing the classical spherical electron model. I'll show that in this example in a second. And then using two intrinsic properties of the electron, e.g. the ratio of two size parameters in an electron model. And I'll show the Bergman-Wesley 1990 model. I mean, bearing in mind that alpha, when measured, can be measured to 1 part in a billion, you sort of have to justify the classes 1 and 2, because I think my personal opinion, only elementary particles are that repeatable and that accurate for you to get the ratio that's consistent. And I mean, we can currently measure to 1 part in a billion, but we might carry on, and we might even get even more accurate. So it seems to be difficult to believe that you could use two intrinsic properties of an elementary particle to calculate something that accurate, and even class 2 is so basically. I mean, it's possible, but I think you should justify your models if you're in the class 1 or class 2 regime. And class 3 doesn't mean you're right, but I think it's just more plausible if you're thinking from an engineering perspective. And if I wanted to create a system which had a very accurate length to length ratio, I would keep it all within one system, and the temperature would be isolated, and all the other influential parameters would be isolated. So that's just a philosophical. I mean, that's not standard physics, but my thoughts on the matter. So the properties of light, everyone knows this. It's a Maxwellian transverse electromagnetic wave with speed c. The speed c is about 300,000 kilometers per second. It can be polarized in any transverse direction. Transverse direction is the direction perpendicular to the direction of travel. The frequency and wavelength are related to the velocity by the simple formula c equals v lambda, and it can be modeled as a photon, as it's done in modern physics. But the photon is only momentum; it's no charge or rest mass like an electron or proton. The properties of an electron: it has charge and assumably associated capacitance. It has a rest mass, mechanical and gravitational. It has a finite energy. That's a total energy. It has a spin, classical, non-classical. It seems to be non-classical, but depends on the model. Has a magnetic moment and associated inductance. And with the capacitance and inductance, the electron can theoretically have a resonant oscillation frequency, V, by the standard LC resonance formula. If not a point particle, it has to have one or more size parameters. If not a point particle, it has to have a shape, sphere, ellipsoid, and toroid. So if you define it as a point particle, you can't define a capacitance. If you define it as a point particle, you can't define inductance, and a lot of classical theory can't be used, which is basically what happens currently. So here we go. Modeling of electron as a point charge. definition of a point, first given by Lucid when he wrote his books on Euclidean geometry and Euclid, pronounce the right name right. And definition of point is that which has no extent or no size. And Boscovich made the earliest sort of modeling paradigm using force points, and that model has basically continued to this day. So if you have no size parameters, you can't scale or indeed calculate alpha from fundamental principles. And the flawed mathematical ratios results with x over 0, obviously undefined or infinity if you like, and 0 over x is 0. It's not useful. Infinite nonsensical classical electrostatic and gravitational energy density as a particle reduced to a point. Cannot even in principle account classically for spin or magnetic moment of electron. Renormalization required in the standard model particle physics of what are called Boscovian points. Boscovich. Boscovian. Oh, I can't pronounce that. Let's carry on. Right. So this is a example of a class 1. I mean, Summerfield did the speeds, but you can do it with the lengths as well. So you can divide the Bohr radius, actually the Bohr circumference, if you consider it as a circular orbit, into the Crompton wavelengths, which is basically the associated wavelength associated with the mass of the electron. So if you calculate that ratio, I mean, both those elements are extrinsic properties. You get the right answer for alpha. Let's go. And if we model the electron as a sphere, I mean, with a single size parameter, so we have to use the radius of the sphere, and there's a classical radius defined, which is I've given it at the bottom of the screen. And we can use the Crompton wavelength again and the classical radius, or the classical circumference, as I put it in the ratio, and again alpha results. So this is a example of an intrinsic property divided by an extrinsic property. Right, now we'll go on to the toroidal ring models. So here you have two size parameters. So a major axis and a minor axis. So the radius of the actual the overall toroid itself is big R, the major axis, and the size of the vortex ring, if you like, or the smaller part is R, which is the minor. This was first introduced by Parson. It's called the Parson magneton. Some people use a vortex model, which is the rotation in the around the ring, but I'm going to discuss the toroidal ring model, which rotates the whole ring itself. The magnetic field of the toroidal ring model will go through the center, and I think the vortex model, the magnetic field has to be contained within the ring itself. So these are charge rings, and the you add all the surface charge up, and you get the charge of the electron E. And I mean, I personally like this this sort of theory, although as we will see, I can't make it work. The theory gives the possibility that instead of an electron orbiting an atom, you can have light going around a ring in a sort of contained in the electron itself, and that the actual space within the electron has as we will see, a different impedance to the impedance of free space. So I'm not an expert on coaxial, what's the word I'm looking for? Oh, come to me. Anyway, so light moving around in, but that's a separate issue. Anyway, let's move on. Right. So alpha in terms of impedance of free space. The impedance of free space is defined by the ratio of permeability over permittivity, and it's about 377 ohms. If we want to create a ratio of two impedances, we can use there's what's termed the von Klitzen constant, which is another impedance, but that's h over e squared. And if we make a ratio of those two impedances with 2 on the bottom as well, we get to a value of alpha. It's very simple. Now, I don't know whether this is slightly different, but I've created this toy model. It's not realistic. It's just how I think things should work. So it's sort of manufactured. So so I've created a notional electron model with a notional inductance and capacitance, and 2 size parameters, lambda 2, lambda 1. Lambda 1 is greater than lambda 2, but it isn't for any particular topology or anything like that. It just works to give something. I mean, it's my wishful thinking how physics should work, and obviously that never works out very well. But if you put these values into the resonant frequency formula, you get a sensible result out. And if you put these values into the what I call the resonant impedance, which is basically L, the inductance over the capacitance, you get alpha out, and that's how I imagine the electron should work. That alpha is a sort of resonant impedance of the impedance ratio of the electron. Whether or not that's true or not, I don't know. It's just my sort of hope. Well, but let's discuss things further. Right. So we'll go back to this notion of the classes of models. So my hope is there is a class 3 type model of 2 intrinsic properties of the electron that will eventually be found. Whether or not I'm anywhere near close to finding it, who knows? But that's my hope. Right. Some theoretical approaches to the fine structure constant. The current mainstream theory, it's fundamental to our understanding of the universe. It seems to be fine-tuned, and when people put in different values in it, they don't seem to get the universe as we understand it, or far from the current value, accepted value of alpha. But we don't have a way of predicting or describing exactly it, other than the definition I've given earlier on. So it's very exasperating. It's fed into the standard model as an experimentally determined dimensionless parameter, or or via other gauge coupling constants. And there is a prediction of it changing in the Standard Model within a very early period of the Big Bang, if you believe that. And it's within 10 to the minus 10 seconds, apparently, but I have no way of verifying that. And so early on, apparently, the Standard Model predicts that alpha changed. Now, if you can create a model like I hope to create, which is very implausible for it to change, then you also kill off the Standard Model in one easy step. I mean, talk about finding weak points. The alpha is the weak point of the Standard Model. There is no accepted theory since the Bohr-Sommerfeld theory of the hydrogen atom was superseded by quantum mechanics, and all we can do is measure it. I've concluded we have to look at historical ideas, non-mainstream ideas, and dissident ideas for further hints and guidance for how to think intuitively about alpha. I should say classical ideas, because these are basically historical, classical ideas of physics. I've listed a few of the things. I don't want to go too in depth, but basically, none of these get to the heart of the matter. The only hope is 8, basically, to unified field theory, because it introduces gravitation into the equation, and mechanical mass and gravitation, and all the others. There's computational approaches by Wolfram and James Skinner. I haven't investigated those very thoroughly, but they're not my type of cup of tea. But they may lead somewhere, and I'm not going to overly criticize. There's numerological models which are just hand waving rubbish, and people can find the alpha in the giant pyramid of Giza apparently, and all sorts of nonsense like that. There's dubious theories about how alpha changed as the universe expands. We can talk about that later. And quantum electrodynamics and current quantum theory don't really have much to say on what the origin of alpha. And this is part of the problem. The hiatus in. Dirac used to say, apparently, when people asked if he would read someone's theory, he'd say, "Have you come up with the origin of the fine structure constant?" And they say no, and says, "Well, come back to me when you have." Because I think his advice to concentrate on this particular thing is really good advice. At least part of your work, and I'm not sure we've concentrated on it enough. So there's all sorts of ratios you can make to create alpha, and 2 energies, 2 momenta, 2 velocities, 2 lengths, 2 forces, 2 capacities, 2 inductors, 2 impedances. Any others? I don't know. And obviously these are real physical ratios, and not sort of arbitrary lengths on the Great Pyramid of Giza, for example, which is basically numerological, as far as I'm concerned. So I've chosen the 2 impedances as my pet theory for today. So the original Bohr-Sommerfeld model was the bound about the electron velocity, orbital velocity compared to the speed of light. It was a relativistic velocity to explain the fine structure in the spectra of hydrogen. Oh, I'll leave this up. I'm not going to go into Helga Krag has written a paper on the history, magic number, a partial history of the fine structure constant. There's various figures. If you're interested in history, I'll put up there. Einstein 1911 you can get from Helga's paper. Michels and Morley actually were the first to measure the fine structure of hydrogen, or basically resolve the very close double lines that represented the fine structure in hydrogen, and they did it with the same device they used to interferometer they used to measure the or not measure the speed of the ether against the Earth. And I think they did that after the famous experiment, 1887 experiment, and I think they published in 1892. I don't exactly the year they published their results, but I think it was 1992. Whittaker is an interesting figure who wrote the history of ether theories, because he came up with this unphysical quantum mechanism, which uses concepts like the capacitance of electron and magnetic properties of electron. It basically, it was unphysical because he had lots of magnets all pointed to with their south poles pointing together and their north poles around, and he did a mechanism that rotated this strange structure of magnets, and it was unphysical because it didn't work under certain circumstances, and then it was dropped. But it's an interesting model to think about, and there's various figures. Arthur Eddington came up with his fundamental theory with the alpha at its center, and George Gamow and Dirac used to argue about how constants of nature changed and their value. And Lancelot White in his Critical Physics basically is an early non-standard form of dimensional analysis. Feynman's made some quotes that people often quote. Honig was interesting because he had his own spherical model. Alexander Unzicker has basically raised the profile of these issues. I find them quite interesting to listen to some of his YouTube videos. And Ray Fleming has an interesting critique of Arvin Ash's fine structure constant video. Arvin Ash represents the sort of mainstream view. There's a thing called atomic units. I'm not sure why I left that in, but it doesn't really change the issue. It uses alpha in the units, but it doesn't change the main issue we're talking about here, where the origin of alpha, basically. Right, so now we're getting to the case study. The Bergman-Wesley 1990 electron model. It was reprinted in 2002 by where is it? I'll come back to find that where it was reprinted by. Right, so it's a toroidal circular current model rather than a vortex sort of anchor ring model. I mean, anchor ring is a term used in the literature of the past to describe a toroidal shape. So the flaws are this: it's no origin of mechanical rest mass. This I'm raising the flaws just so you don't get your hopes up too high. That's going to lead anywhere. There's no gravitational properties. There's questionable origin of the fine structure constant, and the scaling laws of the electron size. Well, that's left unreally answered. So basically, involves calculating the electrostatic energy of a toroid, which is very complicated mathematically, and the formula CE is approximation based on a I mean, the full theory in Moon and Spencer, that's a book on electromagnetism, it uses toroidal coordinates and involves Legendre coefficients associated Legendre coefficients, but basically it can be simplified in approximation to 4 pi squared epsilon naught r over log 8r over r, and you'll get where he got these formulas from the Bergman-Wesley paper. And the magnetic energy can be approximated by a similar formula, but with mu naught r log 8r over r minus 2. And now we're going to try and calculate these two things from they didn't do this in the paper, but I'm just going to show you can do it. Calculate the inductance and capacitance, the root of those two that would be involved in the resonant frequency, and the ratio that would be involved in the resonant impedance. So the frequency depends on the scaling lambda r, which is 2 pi r. So it's basically a major axis size. So, and it also depends on the ratio of r over r, and the inductance L E over the capacitance C, which is the resonant impedance, doesn't depend on R, but only depends on the ratios R over small r. It also has a factor mu naught over epsilon naught, which is the impedance of free space. Now, as before, alpha is defined by half the impedance of free space divided by the a second impedance. I'll put the impedance of the resonant impedance of the electron tube, and we get out this formula with alpha over 2 pi equals 1 over the square root of the log terms, and we can sort of solve it by assigning x to the log term, and we get a sort of what I term the high school level quadratic to solve, and we get our value for x. I missed one here. Oh. Now, in their paper, Bergman and Wesley didn't do that. They basically came to a different way and got r over r equals 8 e to the minus pi over alpha, which is a value of 1.203 times 10 to the minus 187, which is essentially 0. And then they went on to claim that they could calculate the anomalous magnetic moment via making the approximation to the inductance. So at the bottom of the page, I mean, my result of my equally leads to seeming nonsense or very high or low values. And I'm not sure this makes sense at all. But as I said before, this model doesn't include mechanical mass and with gravitational properties, and so I think ultimately, if you're going to go this way, you have to do a unified field theory or construct a way of introducing mechanical mass into the equation, into the model. But on introducing mechanical mass and gravitation into a model, we have to confront the problem of how total rest energy of the electron is to be partitioned between all these forms of energy. A basic discussion on just partitioning electromagnetic energy using a spherical model of the electron was undertaken by William Honig in his 1986 book, The Quantum and Beyond. But I haven't seen many other discussions on this problem. It's not an easy problem, and when introducing relativistic mass or changing as speed increases to near the speed of light actually complicates matters, and this is why most physicists conveniently ignore a finite size of the electron and the partitioning problem that results. It's easier just to stick to Einstein's simplified energy formulas and the notion of point particles. Right, measurement and observations of alpha. I'm not an expert in this, so I've just listed a few, and there's videos online. So if you search for these sort of things, you can actually get the whole video explaining exactly what these experiments will do. But the aim is to measure alpha to 1 part in a billion or better, improve the current state of the art. There's two things which aren't expensive experiments, which is the quantum Hall effect, integer and fractional, which is a 2D. You just put voltage across 2D sample and imply a magnetic field with other things such as keep the sample cold, etc. And we'll see a video on that just to get your feeling of how extraordinary it is to get a measurement that's accurate to 1 part in a billion from lab measurements like this. And there's also a 2D graphene experiment which is alpha turns up in the reflections of light, which, if you remember from your university physics courses, involves the impedance boundaries. The reflectance will occur at a boundary between two different impedances, substance. So that's why I've been interested in impedance, because these two experiments, the quantum Hall effect and the graphene, are fairly new and not really studied, I don't think, in the echelons of theoretical physics. I mean the real top level of theoretical physics. They're all interested in particle physics experiments. Is the particle physics the fine structure constant in put two constants, but basically constant, a constant that's constant in space and time? Well, the standard model predicts it changes its value very close to the start of the Big Bang. But there's two famously. There's two different major theories. There's the particle physics standard model, and there's a the cosmology standard model, standard model of cosmology, and that involves general relativity, and it involves non-Euclidean space. And in basic theory, you can imagine that constant will change if the curvature of space changes in your model. So you'd have thought that the standard model of cosmology would be the one to predict a change in alpha, but it's the other way around. I know. I mean, I'm not an expert enough to know what the reason is for alpha changing. But if like I think the alpha is developed from two intrinsic properties to a very small elementary particle, then neither the non-Euclidean geometry or the standard model particle physics at high energies would the particle collisions at high energies would cause a change in alpha. I mean, that's my intuitive thought. So, I mean, if you can prove that there's no change in alpha, even at extremes of gravity and particle energy, then you would obviously destroy all of physics as we know it today. So that's a challenge for young people to work on. The astronomical measurements of various features of the pulsar, of various other things, they don't show any or measure any exclusive change over time. There's some I can't remember the name of it, but it's a natural fission reactor, and they did I think Freeman Dyson and one or two other people did some work on, and they showed that basically alpha is constant over an extremely long period of time. I mean, the present change is so absurdly small that it's non-existent as far as measurements are concerned. And as I say, the changes that are predicted can't be independently verified. So I personally have doubts. Right. So, Ian, can you come back and can we do this video to basically, it's a video on the quantum Hall effect, and then we'll have a discussion after.
Yeah, certainly, James. Although I think it should basically follow. Do you want to show it from your link, or would you prefer?
Shall I try 2 seconds of it? See,
yeah, I'll stay up while you do it. I think it should work.
Can you hear?
You don't have sound though.
Oh, do I have to make a change to put sound?
Yeah. Do you know what? There's a little tab which said include audio, and you probably didn't click that.
So where's that?
So you'll have to go back to present.
So I stop sharing.
Okay, stop sharing. We start from first principles. Go back to present, and then say share screen. Same thing. Now,
share screen.
And do exactly what you did before. In other words, entire screen, and then. However, there's a little tab there which says also share
audio. All right.
Was that not enabled in your system?
No.
It's enabled in mine.
I've
Okay.
just done it now. So let's try again.
Capital. Yeah. Let's try it. Now, I have to bring it up. Hold on a second. There we are.
So this is a video by Andy Stern, and it's introducing the quantum Hall effect from an expert's point of view.
Introduce you to the quantum Hall effect.
I'll go down now.
Before doing that, I'd like to make a personal comment. To me, the quantum Hall effect is one of the most beautiful phenomena known in physics. If you are in physics for the beauty of science, that's your day. So let's start from the Hall effect. In the Hall effect, in the context we're talking about, electrons flow in 2 dimensions. and the plane in which they flow is subjected to a magnetic field perpendicular to the plane. Now the Lorentz force bends the trajectories of the electrons, and therefore electrons accumulate on one side of the sample and leaving behind positive charges on the other side, and creating a Hall voltage, a voltage perpendicular to the flow of the current. So now we have two voltages, a voltage parallel to the current and a voltage perpendicular to the current, and that makes the resistivity into a 2x2 matrix with longitudinal components and all of diagonal components. So if we want theoretically to see what we expect the elements of the resistivity matrix to be, classically the picture is very simple. The Hall voltage is supposed to cancel the Lorentz force. The Lorentz force is proportional to the magnetic field, and therefore we expect the Hall resistivity to be simply proportional to the magnetic field. Once the Lorentz force is cancelled by the Hall voltage, electrons flow as if there's no magnetic field, and therefore classical physics expects the longitudinal resistivity to be independent of the magnetic field. Now, we are here for quantum mechanics, right? It's the quantum Hall effect. Quantum mechanics, the first thing it does is it introduces two new notions. First is the flux quantum, hc/E, a measure of magnetic flux. And second is a dimensionless number whose importance cannot be overstated, nu, the ratio of the density of electrons, n, to the density of flux quanta, which is B over the flux quantum phi naught. Phi naught is hc/E. Now we could rewrite our expectation for the Hall resistivity in terms of this dimensionless number nu, and the expression we would get, B over NEC, equals to h/E squared times nu. This is just rewriting, and nu is a continuous number, proportional to 1/B. So we could formulate our classical expectation for the Hall resistivity as rho xy, the Hall resistivity, being proportional to 1/nu. Now let's see the experiment. Let's see the quantum Hall effect. So here is the experiment. We see in black rho xy in units of h/E squared as a function of magnetic field or 1/nu. And what do we see? We expected a linear relation. We expected a straight line. What we see are these steps. You see this indicating one of them, but you see there's a step here, step there, and there's a whole line of steps. Those steps are the quantum Hall effect. Now, we expected a straight line and we got steps. You don't get a Nobel Prize for that. You get a Nobel Prize for what these steps are. And let me dwell on that. So, the starting point of each step and the ending point of each step, those depend on sample, depends on material, depend on many parameters. But the value of the Hall resistivity at each step is universal and is constant. What do I mean by constant? What I mean is, if you look at the Hall resistivity at the beginning of the step and at the end of the step, it does not change. It does not change by 1%. It does not change by 1% of 1%. It does not change by 1% of 1% of 1%. It is precise to 1 part to about 10 to the 9, 1 part in a billion. It is one of the most precise phenomena you've ever seen. Now, what's the value at which it is stuck? What is the constant value? Well, those values, look here. What we see here in this main plateau, rho xy is exactly h/E squared. Now that's mind-boggling. It's a resistivity. Usually resistivity is something that depends on material. Here we have a resistivity that is determined by the ratio of 2 of the 4 fundamental constants of the universe. Planck's constant, quantum Hall effect, right? Planck's constant over the electric charge squared. And you see it gets stuck on nu equals 1. it gets stuck on other values of nu, and we will see what values those are. When I say that the value at the step is quantized to 1 part in a billion, here it is. It's 25,812.80745 ohms. It's quite surprising, actually, that H over E squared, this ratio, has the units of ohms. But that's the way it is. So that's the black line. That's the whole resistivity. Now let's look at the blue line, which is the longitudinal resistivity, which is the scale you see on the right here, given in terms of ohms. Now, that's not universal, but it has one universal feature. And this universal feature is whenever the whole resistivity is in a step, the longitudinal resistivity goes down to 0. There is no voltage parallel to the current. The entire voltage is perpendicular to the current, which means, among other things, that there is no heating, because the heating is the product of the current times the voltage parallel to the current. There is no heating when you are in a quantum Hall state. And more than that, as we will see, this indicates something about the bulk of the sample having an energy gap, which also means it is incompressible. Now, what do I mean when I say incompressible? I mean you can change the chemical potential of the system and the density does not change. And we will talk about that more. Now, we saw that there are steps at various values of nu, and I emphasize nu equals 1. What values of nu give rise to steps? So here I'm telling you the outcome of many experiments in some tens of materials, in thousands of labs, and so on. And what we know is that there are 2 types of values of nu at which we get the steps. One is integer values, and I give you some examples here, 1, 2, 3, 4, and it goes up to about 20, 30, that range of integers. And if one type is integers, the other type is probably fractions. And the fractions that we get, that's also a list of about 20 or 30 or 40 values. And here, and you see examples here, 1/3, 2/5, 3/7. You can probably guess that the next one is 4/9. And then you see there's a bunch of them which are kind of the mirror image of the first ones. Instead of 3/7, 4/7. Instead of 2/5, 3/5, and so on. And then there are fractions which are larger than 1, 4/3, 7/5, and so on. And you see all those fractions have odd denominators. But then there's also 5/2, because there's an exception to every rule. So, saying it in a very non-mathematical way, those fractions are of the form P over Q, where P and Q are kind of small integers. You see 1, 2, 3, 7, 11, and these numbers, and Q is usually, for whatever that means, it's usually odd. So this is the quantum Hall effect. The integer values of nu are the integer quantum Hall effect. The fractional values of nu are the fractional quantum Hall effect. What makes this effect so amazing is the precision, the universality, and the fact that the resistivity is determined by the ratio of 2 of the fundamental constants of the universe. I think that this becomes even more striking if we look at the sample at which you see it experimentally. So let's look at the picture. This is the first sample at which the fractional quantum Hall effect was observed. Now look at this. It's so full of details. It has contacts connecting to ampermeters and voltmeters. It has all this dirt, all these white dots. It has all. You cannot reproduce this sample twice in a lab to a precision of 1 part to 10 to the 9. And yet you get an answer from this sample that is precise and that is determined only by fundamental constant. It doesn't matter. This is made of gallium arsenide. But you do the same experiment on graphene, on silicon germanium, on zinc oxide, and lots of other materials, and you get the same answer. There's something here that's very fundamental. And this is why we are going to talk so much about it in this course. You see that, as I said, in lots and lots of materials. And this is just basically a random collection coming out of looking at Google Images for quantum Hall images. But I'd like also to use this presentation to mention that there are conditions to see the quantum Hall effect. You usually need low temperatures. You usually need pretty strong magnetic fields. And not very, very strong, but not the level of the magnetic field you use to stick a pizza sticker to a fridge. And you need clean samples, not the ones you would produce in your study. But other than that, you have a universal effect here.
We need cedar.
So as we saw, there are integer values of nu, the integer quantum Hall effect, and there are fractional values of nu. Some features are common to both, to any quantum Hall state. Other features are different, very different for the integer versus the fractional. And I'd like to give examples to both. So one example that's common to both is if you look at the longitudinal resistivity, I said that it's 0. But in fact, as you measure it more and more precisely, 0 is never exactly 0. You see that its temperature dependence is of this Boltzmann type of form or Arrhenius type of form. It's proportional to the exponent of minus T0 over temperature. So you can see the resistivity or excess going down by several orders of magnitude when you change the temperature by about 1 order of magnitude. That is an indication of the existence of a gap in the bulk of the sample. In contrast, common to all quantum Hall states, integer and fractional alike, and something we will talk about in great detail in later segments in this course, the edges of the sample are never gapped. They are always gapless. And you can see that in the plot downstairs, where you see in the upper half the longitudinal and Hall resistivity, and you see all these great happenings, things changing very dramatically as you change the magnetic field. But then in the lower part of the sample, you see the tunneling density of states into the edge. And you see that it's never 0. It changes here and there, but it's never 0, because there's no gap at the edge. So those are two features which are common to the integer and fractional quantum Hall effect. Now let's talk about features which are different. And there are two I'd like to mention. First is what gives rise to the effects. The integer basically needs the Pauli principle, or the Fermi statistics, needs the fact that electrons are fermions in order to exist. It can exist both when the electrons interact or do not interact. The fractional quantum Hall effect needs electron-electron interaction in order to manifest itself, in order for fractional quantum Hall states to be created. That's one difference. The second difference, so beautiful, so much a subject of one of the segments we're going to see later on in this course, is the world of fractional excitations. It is the fact that in the fractional quantum Hall effect, electrons break into quasi-particles whose charge is smaller than the charge of the electron. Those quasi-particles have unique properties, fractional statistics, all kinds of other mind-boggling properties, and we will see those. Generally, when you see an effect like that, you can imagine 4 directions of research you may attempt in order to understand or in order to enjoy this effect. The first direction is you can ask yourself, why does it happen? Why do we get this precise quantization? Why do we get those particular value, 1/3, 2/5, and so on? And we are going to talk about this in the context of the theory of the edge, Lattinger liquid, and also a theory of the bulk when we talk about composite fermion theory. That's one direction. A second direction you can imagine thinking about is, let's forget the question of why does the effect happen. It happens. Everyone, it's seen in thousands of experiments. It happens. What we can try and understand is, what does it tell us? Combining this observation that we just saw with other things we know about physics, with charge conservation, with energy conservation, whatever, what conclusions can we obtain? And we will talk about that too. We will talk about fractional charge. We'll talk about fractional statistics. And we will talk about implications of the effect on localization. All those we will discuss without even understanding why the effect occurs. So the third type of questions we can think about is, does this type of effect occur elsewhere? So maybe before trying to think about that, let's define ourselves. What do we mean by this type of effect? Well, we'll do it from the mathematical angle. You know that when you find a new physical phenomenon, you need a piece of math to try to understand it. With the famous example of Newton and the apple falling on his head, we know that he needed the mathematics of differential equations in order to describe the motion of the apple. The poor guy needed to invent it. But we live in a luxury of a much more powerful mathematics nowadays. So we need to find the right branch of math to analyze such an effect, where there is a physical phenomenon that does not change as we change some physical parameters, such as the magnetic field, as we saw here. This branch is topology. So the quantum Hall effect is a topological state of matter. And the question we'll ask here is, are there other topological states of matter which do not require two dimensions, which do not require magnetic field, and which are different? And the answer is yes. We will talk about topological insulators, we will talk about topological superconductors, and we will talk about topological semimetals. All those will be part of future parts of this course. And last on my list here, is, can we make use of the quantum Hall effect in one way or the other? Now, there are two uses I'd like to mention. One is almost obvious. If you have an experiment where you measure resistivity, the Hall resistivity, and you get the same answer to 1 part in a billion, you can use this experiment in order to calibrate your units, in order to define what the ohm is. And indeed, this is nowadays done. So this is a present use. Far into the future, you can think of using the quantum Hall effect or other topological states of matter in order to realize a quantum computer. And in this particular case, in order to realize a topological quantum computer. That's a very futuristic vision. And we will talk about it also in this course. So to summarize this segment, we saw the quantum Hall effect. We saw the integer quantum Hall effect. We saw the fractional quantum Hall effect. We saw the precision. We saw the universality. We saw the reproducibility. And we saw how fundamental it is, having the Hall resistivity quantized to h over e squared, two fundamental constants divided by nu, with nu being a very clean dimensionless number. Thank you. I hope to see you in the next segment.
You're back, James. I don't know if you want to finish off, or is that it? Would you like to say a few words in conclusion?
We'll just finish there because we're running a bit late. So I think that made my exam.
I'll give you some time.
Sharing. So I've stopped sharing. That's it. Yeah. So basically, that sort of amplifies my position that how can you measure a variable to 1 part in 10 to the 9 in a macroscopic sense. It's definitely associated with particle physics, or very close to particle physics, as those numbers only appear in when we're talking about the atom, we're talking about even smaller than the atom. So yeah, that's the point I'm trying to make, and that's the question I'm trying to raise. I hope there's some of that has come through in the introductory talk on the fine structure constant, and the follow-up talk on the quantum Hall effect. That's it. Questions?
Well, thank you very much. I think that's quite illuminating. It's quite obvious that you've done a considerable amount of work in this area, and you've brought together a lot of,
I still don't understand it.
Well, disparate phenomena, all the slides, there's so much detail there, and a number of comments have come in saying that you've lost them a bit, but I'm not surprised. And the recording, as usual, will be available for all time, so people can do that, and luckily they can pause the recording at any of the slides and have a look at those two things. I certainly like the idea of the ratio of the two impedances, or half the value, in this. The other thing I just very, very quickly is Sir Arthur Eddington in The Expanding Universe. Now, I know the book is about 80 years old, but he said it is possible that the fine structure constant is exactly 1/137 rather than approximately. I don't know if you have any views about that. Do you think that's superseded?
Yeah, well, all these last books running up to the fundamental theory book, which was published after he died, basically it was all running towards that theory that everything could be given by integers. But now we know the fine structure constant to so many decimal places, and it's not exactly an integer. It might be a rational number, but it could well be a number like pi, which is a notional number that comes out. I mean, pi has infinite digits, so we can never know it in a physical sense, but it seems to arise in our geometries. And I'm wondering whether the fine structure constant has a similar, but we don't know at the moment. But it's certainly wrong that is an integer. He was wrong. But a lot of people.
Are we not talking about maybe the ratio of these quantities to the units we adopt? I mean, if we adopt a unit of 1, well, then pi is a transcendental number. But if we adopted pi as the unit, well, then it would be exact, and 1 would be 1/pi, which would be transcendental.
Well,
however, while you're thinking of that, I'll just very quickly go through the comments. We don't have very much time, and I want to give a bit of time for one or two people to come in, at least from the green room. I think James has been making a lot of comments.
I know. I apologize to James because he has a theory, but I with a limited time, I looked.
I don't think we can go into all that.
I couldn't.
I mean, it's quite obvious. It's quite obvious that Jim has counter views to yours,
yes,
and that's fine. That doesn't
exactly.
mean he's right and you're wrong. And also, he's quite complimentary, or at least his views concur with Professor Stearns there. We'll come to that in a moment. Let me just see. I'll just go through this very, very quickly, and I apologize if I miss anything. If I do, just repost the comments. Say, look, Ian, you missed such and such. Okay. Reduce Planck's constant and so on. Okay. They're mainly comments backwards and forwards between question and fractal woman and Kelvin and so on. A lot of comments here. Toby Gross. I
mean, James Keane has made the comment: unified field theories apply the two wrongs to make a right. I mean, I'm not sure that's Correct.
Could we come to that in a minute? Let's just get rid of the main comments, and then we'll deal a bit more detail with James's comment, if that's all right, James. Two Jameses. So is saying from Tawari's space vortex theory, the fine structure constant reduces approximately to, I'm not quite sure, it's a pi 2 rather than 137, showing thereby that there is no special significance to the number 137, except that he's gone more here actually. Except that it could be a cumulative experimental errors in experimental determination of various constants. Yeah, I don't know. Experimental error. I think that's one of the things actually James has also written about. So unless you have any comments.
I mean, thousands of experiments. I normally criticize theorists in the highest echelons, but I can't criticize thousands of experimentalists, people, engineers and applied physicists. They're not going to get this sort of thing wrong. So okay. There we are. That's partly why I put the video there, just to add some sort of there is all these experiments that hopefully theorists should make a bigger effort in trying to explain more coherently and more understandably.
Okay, well, I'm about halfway through the comments. I'm going through them very, very quickly, so there should be enough time to go into a bit more discussion. I wanted to give you time to devote to some of Jim's points rather than just, make one or two comments during the time that we're looking at the questions. Okay. So if that's acceptable.
I mean, Ian, what's your thought about putting everything defined and then just putting a unit system just based on alpha and because in your day, presumably it was just the speed of light which was fixed, right. And you hadn't got a thought yourself on that trend.
And all these natural units and Planck lengths and all those sort of things. I don't deal very much with those, James. I don't know. Perhaps. I mean, again, Eddington has said that a lot of our so-called science is just convention. So he even said it could be argued that the Newtonian system of dynamics, which works, is no more true than the metric system is true relative to the imperial system. And then he quotes Pope, or he changes Pope's statement or in poetry. Nature and nature's laws lay hidden night. God said, let Newton be, and measurement was facilitated. He said it's only a convention. So it depends how you look at it.
I mean, when you can measure the quantum Hall effect to 1 part in a billion, you sort of obviate the need for a £1 million standard lab, don't you? So you can have a standard lab wherever you want it and a relatively low cost. I suppose that's the idea, but
it's ubiquitous.
It's a very, very big change. Yeah.
Okay, just very quickly, he's asking, it's a bit tangential, but do you accept relativity, probably Einsteinian relativity? I think you accept the Big Bang. Just maybe, it's not really relevant to your talk today, but just a quick view of your own perception of those.
Well, maybe. I gave a talk on my understanding of relativity in terms of dimensional analysis. And basically, I came up with another scenario which also agrees with the Michelson-Morley experiment, so and other experiments, and it doesn't involve mixing up space and time. So I do believe in relativity, but not in the Einsteinian sense. But but the problem is I haven't had time to work out every dot and underline every cross every T. So it's a work in progress. So I can't say that people should learn it. I'm just saying there is mathematically an alternative to the Einstein framework, which needs to be studied to see if it makes sense.
Sorry to put this in now because we're coming to the
at least one
green room, but just really a bit of a question some people might be concerned about or interested in. You have your own consultancy company.
No, that's closing now.
Is that closing?
Yeah. So
Well, the reason I ask that is a lot of this research work you're doing, I mean, it's quite deep. Is just for your own interest, or are there any, repercussions from the point of view of consultancy?
See, when I was I started off studying engineering, and then I only did 2 years of that in the end, with the gap, and then I took up physics, geophysics. So it's not really full on quantum standard model physics, but since then I've been interested in this the difference in outlook between an engineer and a physicist. And when you look at the historical record and the historical written record of physicists, they're much more engineering orientated, understanding from a classical sense, than the modern. And I've always been interested in that dichotomy. So I'm interested in the philosophy and the history and why we believe what we believe. So I'm not really a physicist. I just try and open up people's minds with a can opener to try and say, well, what if you think this way? Where will we lead? And obviously, in this talk, I've proved that we lead into a dead end. But these matters are so big and so awesome that people should keep on trying. That's the basic summary of this talk.
So just the very last question, and people, if they're posting things from now on, I'm sorry, we won't be able to deal with them. The very last one, Jim Morrison says, or he asks, if C is a function of gravitational potential, would that affect the value of alpha? The speed of light?
No, because alpha is, especially if it's two intrinsic properties, they're guaranteed to be in the same frame. And when you're in the frame, you can't have two speeds of light. The speed of light is constant in a frame. It's only when you're comparing two frames. I do believe the speed of light changes with the moving frame, because I believe you have to look at my other talk to explain why. But basically, within the frame, C is constant, and then because all measurements are ratios, everyone comes up with the same number, which is a measurement in all the frames, even though the actual physical quantities before they're measured are different. They're different in size, but because you measure it, it's all down to dimensional analysis, and I did that in the talk. When you compare two,
would it not be more a function of things like the permittivity and the permeability of free space that would come in and they're basically fixed?
Well, that's a different matter, because that they set the speed of light, yes, because the relative, if you're in the classical sense, in the relative permittivity and relative permeability, set a speed of light in a material different from the speed of light in a vacuum. And I didn't really introduce that in the concept of a relative permittivity and relative into the talk, but in one of the in my analysis of the model that failed, the Bergman-Wesley model, the ratio of the two impedances, the relative permeability would cancel out if you compared it with a space of relative permeability. So I'm not sure how that would cancel out the equation, just as the free space would cancel out. So you probably want basically a theory that has complete cancellation of relative permittivity and relative permeability to get these guaranteed constant numbers that they're
then
getting.
You'd have a different speed of light if they didn't cancel out.
Okay. Yeah.
Well, time is pushing up on us as usual, catching up on us, and I think I'd like to bring James Keane in, because he's made a lot of comments which are very interesting. But I know he has his own hobby horse, if I may say so. It's his own theory. He's put a lot of work into that, and he'll be talking to us, and I think maybe next time on that. But he's rather interested in that, and he seems maybe to be saying, if I may try to paraphrase it without doing him an injustice, that his theories are very much at variance with a lot of what you've said. So, Jim, you're up now, and if you'd like to highlight a couple of things.
Well, actually, I'm very much buoyed by James Atherton's, if I pronounce that right, sir, presentation. Yeah. Thank you. Because basically, I would perhaps rename the presentation "Why efforts to understand alpha have failed." and so I'm very happy with your presentation.
Well, that's a subtitle, yeah.
Right.
Yeah.
On, so,
cheers.
But you also say, don't you? Sorry to talk loudly, but that the Professor Stern, his theories are more consonant with your own. I think you said that in the comment.
Well, yeah. I mean, Stern, it's sort of inevitable that Stern is going to become a binary, if not already, is a binary mechanics advocate. He was even talking about fractional charge, to his credit, so that the only place you're going to find a complete treatment of this subject is in binary mechanics. And this requires full quantization. And so that's the final step that's necessary. But I'm really happy and buoyed by James's presentation today, because he really summed up, a story of abysmal failure of mainstream views. And so
the theoretical failure.
You did a good job there. Now,
well, hopefully,
as a neutral moderator, I think we can all agree with that statement, Jim.
One of the fundamental things is that go ahead, James. I'm sorry.
Sorry, I just say.
Were you going to say something, James?
I hope it hones your presentation in trying to address some of the points that I've not made clear in this one, and that's made more clearer by your theory. Perhaps that's what I was going to say. In your future, because I understand you're not going to make
very clear now. I think you've been very clear, and I thank you for that. Now, one comment I might make is this problem with you or Stern, I forget who, was talking about the fundamental constants of nature, such as electron mass, Planck's constant, the speed of light. All of these are not fundamental constants, and in fact, they could not be, because they're not orthogonal. They don't provide an orthogonal basis. The very equations that you presented showing interrelationships among these constants have a definite meaning. They're stating that you can express each one in terms of the others. And what this means is that they're not orthogonal, and therefore they actually could not be fundamental. So then the question remains, what are the fundamental constants? And the primary constants that binary mechanics has determined do provide an orthogonal basis for proceeding. So that that's just one point I might highlight in terms of this story of failure. Part of the story of part of this history of failure is the failure to recognize that what are called fundamental constants actually are not fundamental and could not be fundamental. And it's simple algebra. You know, it's amazing that physicists seem to be a little weak on math. You can look at these equations and see that these items are not unrelated to each other. And so therefore, there's a shared variant, what we call a shared variance or redundant information. They don't provide what mathematicians call an orthogonal basis, which the primary constants of binary mechanics do. So my final comment, because others, Ian might want to bring up others, my final comment is that I'm very happy today, and it looks like what you presented, what Stern has presented, makes acceptance of binary mechanics unavoidable and, in fact, inevitable. I mean, there is no other alternative. Thank you.
Well, the only thing I would say, maybe in summary, there, if I may, is that we're most happy to have a sort of a continuity between talks. So, in other words, you, Jim, I'll call you Jim and James. Jim is a regular participant in our systems, and obviously, a lot of what is being said, in particular what James has given today, will feed into his subsequent lecture, which he's going to give us shortly. And similarly, James has no doubt been enlightened by a lot of the comments that we've made. So we're very happy for that to be the case.
Yes, indeed. Thank you.
So thank you very much, Jim. Thank you for that.
Yeah.
Well,
James, anything else before we might have time for one more contribution from somebody. Most people actually have left. I was going to ask you, Denny, but Denny has put up his hand, so it's even better because you have some points which are always very valuable. So, Denny.
Hi, Denny.
James, Dave Bergman and myself have gone on from the Bergman-Wesley model to another model, which is not a two-dimensional object. It's three-dimensional. It's a donut as opposed to a torus. And that is to say, the interior is not empty. And this model is in complete equilibrium for all forces. And it's composed of two types of energy: electromagnetic energy integrated throughout all space in and out of the model, and magnetic energy integrated throughout all space in and out of the model. And the magnetic energy is F when divided by squared, and the electric field energy is gravitational mass when divided by c squared. And we have what we call user friendliness, which means that there's no discontinuities when it's in equilibrium. And we just use ordinary Wesleyan EM theory, which is, however, different from what you find in classical electrodynamics by D. Jackson, for example. And he has chapters 4 and 5 in his book, Scientific Physics, where he goes into his particular electromagnetic theory. And that's the same Wesley as the Wesley-Bergman model. And they use penning traps to measure the electron's properties. I'm sure you've probably heard of this.
Yeah, it was one of the experiments.
Our model is for an electron that is alone in space, whereas the penning trap uses magnetic fields to hold the electron captive. So that explains why we don't get free the alpha. We get a different number because ours is for an electron in an empty space, not in a penning trap. And we just can do this for protons, positrons, and negative protons. And when you normalize all these, you get the same very simple question involving only one integers with 4 of them. And we call that a normalized soliton. And I can send you, give me your email address. document
Yes, I think I'm on the list of people.
Electrons.
Well, Ian's got my email address anyway. So if you're not on the list,
I can send you the email address if you want, Danny.
Yeah.
Yeah.
Okay.
By the way, I did omit to mention. I'm sorry. I apologize. When James was discussing case study A, the Bergman-Wesley model, that Denny here, who's speaking to us, Dennis P. Allen, has spent many years working with the late David Bergman on the model, which he's now talked about as being superseded by later work. And also, he's done considerable work analyzing Wesley's work in electrodynamics. In fact, he introduced them to me, and I've spent some years updating some of my ideas based on Wesley's ideas. So I do thank Danny very much for that.
Yeah, one thing I didn't mention is that the whole idea of the Bergman torus model is that you get a pinch effect, i.e. it's a magnetic bottle for the electric charge. So it doesn't, because electric charge, if you have a sphere or even a torus, if it's not contained with a magnetic field, it will explode outwards. Or if it's not contained with a some sort of other force, you'd added like what do they call the Poincare stresses or something like that. So that's the interesting part about the model. The fact it doesn't work is a shame. But anyway, but I'm glad you've tried to work on it and improve it. It's an interesting model.
Well, thank you for that. Anything else, Danny? Before
yes, well, it's in complete equal, James, Arathoon. Our model's in complete equilibrium force-wise. And the charge is held captive by a pinch effect of the magnetic field since the charge is rotating or about the ring. Excuse me.
Well, I'm not sure that it works, but if, for example, if we had a sphere, the only way for a sphere to
have to take a look at it.
The only way for a sphere to be stable is if there's some sort of other force, a gravitational force that reduces the energy density of the electric field, and the only example is a 1/r.
Yes, it can't be a smooth or out.
It has to the gravitational adjustment has to disappear at large lengths from the sphere, because that's all we see is the electric field. So there has to be. I mean, I like models, the early models, which are static models of the atom, because they brought this 1/r effect, and it's basically summarizes the basic form of the quantum theory. There is a sort of 1/r change in almost like the permittivity and permeability of space, the actual energy density of space, away from masses, the mechanical mass, the gravitational mass, whatever causes that, changes the electrical properties of space as well. But I that's a thought I have, but I can't put that into sort of concrete numbers, and so it's not really got something that I can present at the moment.
Dave and I have calculated all the numbers that are relevant, all of them.
Some of those papers which were published, maybe, Denny, in Common Sense Science or something, if I'm not mistaken, which you've sent to me. I don't know if James is familiar with any of those.
Yeah, one of the diagrams is from Common Sense Science, but when I've searched for the website, it's disappeared now, so I'm not sure
Okay.
how you get hold of.
Yeah.
hold of.
Well, I after this talk, I might just send an email to both of you, just to introduce you to each other, so you have their email addresses, if I may. So thank you very much, Danny, for that. Is that okay? I'll bring it down now. Thank you for those comments. Now, with everybody's permission, we're coming near the end. If I may, just before wrapping up and giving James an opportunity of coming back just to wrap up, if I may just indulge your patiences a little. We have this current thing which is available at the beginning of the year on fundraising, and unfortunately it's about filthy lucre, just keeping the CNPS running. So if I may just play a very short presentation by David de Hilster on it, and then we'll come back and wrap everything up.
Hello everyone, I'm David de Hilster, president of the John Chappell Natural Philosophy Society. During the past 2 years, we have used annual fundraising drives in order to keep our organization's presence alive and well on the internet. Both years we have been successful in that the monies collected have been enough to keep us afloat. This year is our third annual online fundraiser, and once again we are counting on your support. But first, I want to thank everyone who pays their annual memberships through our automatic online system. Your support is vital and provides us with important funds to keep the CNPS afloat. Hopefully, as we continue to grow, we will be gaining more and more automatic memberships so that these fundraising events won't be necessary. But we are not quite there yet. This year, we will be implementing several changes to our online system. Several to save money and lower our annual expenses, and another to better our discussion platform. First, we will be moving our websites and databases to another server that has graciously volunteered to host us at a much reduced rate. It currently costs us $1,400 a year for our dedicated server, given that we need complete control over our own software. The new server will give us and allow us that control, but only for $250 a year. Second, we will be moving away from BuddyPress, which is a Facebook-like plugin for WordPress, to using Discourse. BuddyPress was an interesting experiment, but the upkeep of the plugin and its general design don't really fit what we need. What we need is a robust and well-accepted discussion forum, and that is why we'll be moving our online discussions to Discourse. It costs $20 a month, which is half the price of BuddyPress. I think those currently active in our online discussions will find this new platform much more enjoyable and functional. Third, we are moving to a free version of Overleaf, which eliminates a $33 monthly fee. Overleaf was useful for us when we were publishing our own proceedings for conferences, but that is no longer needed. Our goal this year is $2,000, and I hope we can reach that goal. Whatever amount you can donate, it is greatly appreciated and needed. Your membership and donations are vital to keeping our online community of critical thinkers alive and well. To donate, go to fund.naturalphilosophy.org. That is fund, F-U-N-D.naturalphilosophy.org. Thank you, and keep up the amazing work that is driving science forward.
Well, thank you so much for your patience with regard to that administrative but necessary message. Now, James, just before we finish, because again, the clock is caught up on us, I'm going to give you the sole floor. I'm going to put myself down to give you an opportunity just to spend a couple of minutes, if you wish, just summarizing what has happened, what you've said, maybe in the light of any of the questions that have come up, maybe unanswered, or maybe in regard to what might be appropriate for future presentations and discussions. So I'll just give you as long as you want to finish off, and then I'll come back and officially finish the meeting.
So there's a summary of the talk about the fine structure constant and how fundamental it is in our both measurement science and our theories. I've tried to explain that we don't know much about the nature of the fine structure constant, whether it's a a rational number or an irrational number, that some basic fundamental constant of geometry like pi. And I've tried to explain how I think there is three types of classes of model, where basically you create a ratio between two values with the same units, physical quantities with the same units, to create the fine structure constant. And those two can be two intrinsic quantities to the electron, one intrinsic and one extrinsic to the electron, and two extrinsic to the electron. And I favor the two intrinsic parameters of the electron, but I haven't obviously given a model yet that is satisfactorily proving that. But it's an interesting thing, and I believe if people go with two extrinsic quantities or some in between state, they should have to justify it. Why does it produce this value which doesn't change by 1 part in 10 to the 9 in our measurements, and in theoretical change in 1 part in 10 to the 17? It's just amazing constant. And that's what I finish. Yes, thank you very much. Cheers, Ian.
Well, thank you so much, James. And I thought today's lecture was actually really one of the best we've had for some time. It was very clear. I know some people in the comments have said it was beyond them and so on, but we don't expect everybody to have studied this in the depth that James has. James has done a lot of basic work, and he also has given us the opportunity of looking into that, giving us a summary of all the work that he's done. Obviously, this has been over a period of years, if not decades. I'm sure one wouldn't have amassed all this information. He has been admirable from the point of view of dissident scientists, in that he hasn't been dogmatic. He's told us quite clearly where we don't know what the situation is, and how it may or may not be this, and how we might go forward to get more information to give us a more informed position with regard to all these phenomena. So I'm extremely impressed with the information, and of course James is we're multiply indebted to him for the various lectures he's given us on things from the Hippocratic Oath to the charge and mass, the alpha, and my hobby horse, which is sort of historical science, the Alfred O'Rahilly business, which he's promised to give us a talk. We have that noted down, and so we're looking forward to having him back for the future to give us talk. So on behalf of the society and all of us dissident scientists, and indeed people who are participating who are more mainstream, I'd like to thank James very much for the trouble he's gone to provide all those very, very detailed slides. I got a little warning from Denny, actually, that he got a message, this may not be recorded. Now, I hope that's untrue. I very much hope that we haven't lost this. I think we'll check that afterwards anyway. So we do get erroneous messages like that sometimes. So again, it's just coming up to the time when we must close the meeting. I shall close it now, and we look forward to seeing you again at the next sessions. And if you have any particular questions which haven't been answered or concerns, do get in touch with us. I'll be putting Denny and James in contact immediately. So nothing more to be said. I'm almost speechless, actually, with the amount of information that has been conveyed to us today. And we're so very grateful to James again for having come back and given us the benefit of his analytical mind. So I wish you all, wherever you are on the earth, a very good day.